do today. So perfect timing.
All right.
Okay. So we're basically going to take off on transformations of exponential functions today. So kind of like what we've been doing in lots of our other outcomes up until this point, right? Like the A, the B, the H, and the K, all of those pieces that play a factor in shifting our graphs up and down and left and right and stretching them vertically and horizontally and then flipping them, reflecting them about the vertical axis and the horizontal axis. So all of those pieces, now we just get to do it with a different type of graph. Our graph now is going to be exponential functions, okay? So are you guys seeing my set of notes?
Yeah.
Okay. All right, so if you do have the set of notes, this will be page 3 in your set of notes. And all this is it just kind of recaps everything that we've done from previous units. So talking about, hey, if we're looking at, holy doodles, I've got people, my remind notifications just went off like crazy. Okay, we're good, we're good. So A, again, just if we go back to your basic of what it's set up. So if we're talking exponentially, we've got a basic function that looks like so, right? Y is equal to c to the power of x. So c being just the base of our exponent, right? We've got our base to our power. So that c, you notice, is going to show up in your general equation. So that's just whatever that value is, whatever our base is, to whatever power we're going to work with. Now the a, there'll sometimes be a value in front of our base, which will still indicate whether or not our graph is going to stretch vertically. So it's going to show if we have that vertical stretch. And if it happens to be negative, if we have a negative a, then we know we're going to have that vertical reflection, right? So this would be considered, we could just simply write it as a vertical reflection if your a value is negative. Now B is the one that's showing up in your general function, up in the power, up in the exponent. It'll show up in your, up where your x is, and it's going to be out front of your x. So in that case, that's going to show us our horizontal stretch. And then we're going to see that if B happens to be negative, you're also going to have a reflection. This time it's going to be a horizontal reflection. Okay. So that means it's horizontally reflecting. So it's looking like it's crossing your y-axis as it reflects. Now K shows up, that's in your general function. It's the end product that we've got where we're adding whatever value. It's not up in your exponent, it's added on the end. And that K, just like before, is it showing us as a vertical translation. So it's basically telling us if we're moving up or down. Okay, so this is just telling us if we're moving up or down. And then the H, so the H is actually going to show up in our general equation up in our exponent. So it's going to be up where your x is. So up in your exponent up here, it'll usually, it'll show as an x. It might be like a +3, it might be a -3, whatever that is, it's going to show up in the actual exponent itself. So just like in our other units all the way along, it's going to represent, it's going to tell us whether or not our graph is going to shift left or right. Okay, so if we're looking at this, this is basically we're shifting left or right. Okay, so all of these pieces, these are all things we saw in our very first outcome that we worked on. We saw it again in the second outcome that we worked on. So these are nothing new. The only new piece that we're pulling in is the type of function that we're working with. We're just changing our function and changing it to an exponential function, okay? Questions at this point?
Sorry, Josh here. I had a question.
Okay.
Is the reflection always going to be
like this, the reflection point going to be where it crosses the y-axis?
Only if you're dealing with a reflection, a horizontal reflection.
Right, but the horizontal reflection will always be at the y equals or x equals 0.
Yes, yes, because it is literally reflecting about that y-axis. Absolutely, right? So a horizontal is going to shift across your y-axis, where a vertical reflection is going to shift. It's going to reflect about your x-axis, right? It's going up and down. Yeah,
and that's reflecting off whatever your asymptote is.
Yes, yes, absolutely. Yeah, because if we're going to get to the point where we may shift something up, right? So we could potentially move our asymptote up here. So our graph could be looking like that. And then if we had a reflection, and I should have did it up this one. So if I did it here and then did a vertical reflection about it, it wouldn't be reflecting about your x-axis. It would be reflecting about that asymptote. Yeah.
Okay. Thank you.
Yep. Okay, so let's put some of these into practice then. Let's have a look at one and try it. And let's work through the whole process and trying to make sense of what happens to our graph as we do this. So like yesterday, we have to essentially, when we go to graph these and apply our transformations to them, we have to identify what our base exponential function is. Meaning then, before we do any transformations to it, I want to know what the original graph would look like. So it's about identifying where is your C in this instance, right? Where is that base of our exponential function? And you're always going to identify where your exponent is. And then the number in front of it, which will represent your base, actually creates that original function. So really, my original is not the 2 in front, it's the 3, that base of 3 to the power of x. So my original exponential function is solely whatever that base, whatever that value of c is here, because this 2 out in front, that's representing your a value. That's your a in there right now. And then this is all up in your exponent. Okay, it's all up in the power, and you don't technically have anything being added or subtracted after the fact. So once we know what your base exponential function is, then we can use that to start building on. So we're going to use that original function to create a little table of values of some basic coordinates that we can use then to manipulate to create our brand new coordinates based on our transformations that we have going on. So like we did yesterday, we're going to take our x and our y, and we're going to pick values -1, -2, 0, 1, and 2. And we're going to start figuring out what y equals in all those scenarios. So when I look at this again, I can start with, if I start with the positive side of things, because looking at the positive exponents sometimes are easier first initially when we're working with just a basic function here. So 3 to the power of 2, we know that's going to make 9. And then 3 to the power of 1 is going to make 3. And 3 to the power of 0 makes 1. And now remember yesterday when we were talking about, if I've got this as 3 to the power of a -1, I want to make it a positive exponent. So that is going to bump that 3 to the power of 1 down to the bottom. So I'm actually working out to making that equal to 1/3, which means then 3 to the power of -2 is equivalent to saying 1/9. Okay, are we okay with that?
No.
Okay, so once we've created that base function and got that basic exponential function, this we're going to utilize to create a brand new set of ordered pairs. Because ultimately right now, what we've got on our graph is I've got 0 and 1 is going to end up here, 1 and 3 is going to end up here, and 2 and 9 is going to show up here, and then I've got the -1 and 1/3, so just above the x-axis, and -2 and 1/9 is getting closer to that x-axis, but it's not touching it. So you start to see I get this lovely exponential graph that looks something like that. Okay, so that's my original graph. just of my basic y is equal to 3 to the power of x. Now I want to know what am I going to do to this graph in order to satisfy my transformations that I've got. So right now I've got a is equal to 2. That 2 in front is representing, if I go back to my original, right, if I've got my general idea of okay, so my general equation of an exponential function. So that a, that's representing a vertical stretch. So anything, so if I'm thinking in terms of x and y, that vertical stretch, that's going to affect my y, okay? It's affecting y by a factor of 2. So that means every single y value that I have, it says by a factor of 2, I'm multiplying my y's by 2. So every single y is going to get multiplied by 2. And then I look at, so that's one of the numbers that I have to worry about. And then the other one is this 4. I've got x minus 4. Well, that's showing up in the top part of up in my exponent. So that looks like it's talking about my h. So it's saying h equals 4. So in this instance, that h represents a horizontal translation. That's telling me that I am moving left or right. Now, it's always the opposite of what we think it is. So it's saying x minus 4 right now. So the opposite of, we think, like initially we think, oh, that's moving us to the left. It's doing the opposite of that, and it's actually moving us to the right 4 spots. So that means every single x value that we have, we're going to end up adding 4 onto it. So now what I start to do is I create this little mapping notation, and it's basically telling me exactly what I'm going to do to every single x and y value that I have from my original set of ordered pairs. So what I can do from there is create my new set of ordered pairs based on this information. So now we're saying, hey, well, if x is -2, that's my first ordered pair. If I put a -2 in for x here and add 4 to it, I'm going to get a +2. And then if I look at my y, well, every y, I have to multiply it by 2. Well, if I take 2 times that 1/9, that's going to give me 2/9. So now I've already established my first new point, okay, of my transform function. And I go ahead and I do that for each of them. So I put a -1 in, I get a 3. I put a 1/3 in and times it by 2, I get 2/3. I put in 0, and I put it in 0, I'm getting 4 for x. And I put a 1 in, I'm getting a 2. I put a 1 in for x, I get 5. I put a 3 in, and I get a 6 for y. And last one, I put a 2 in, and I get a 6, and I got a 9 times the 2, and I'm coming up with 18. So your last step in this is essentially, let's go through and let's graph this. So I'm looking at now, I've got 2 and 2/9. So I'm above my x-axis, but just barely. And I've got 3 and 2/3. So that's a little higher off of my x-axis. And I've got 4 and 2. And I've got 5 and 6. 1, 2, 3, 4, 5, 6. And then my last one is 6 and 18. Okay, that's going off my graph. So I'm just going to place a dot up here, and I'm going to label it as 18 and call it a day on that one. So really, my new graph is showing up like that. And I would end up labeling that one as y is equal to 2 times 3 to the power of x minus 4. Okay, so I would just label it as what my original function, what I was trying to graph initially. So when we think about it, we've stretched these points. Every point we've multiplied the distance in between by 2, and we've actually shifted this graph to the right 4 spots. So every point moved over 4 units. Questions? Okay, so have a look at your domain. Let's have a look at your range. And let's still think about what your horizontal asymptote is. And if we have any x-intercepts or y-intercepts, any intercepts at all. So our domain, just like yesterday, we did no reflections to this at all. So really our graph still looks the same as a basic function one. We just literally stretched it and just moved it over, shifted it sideways. So my domain, there are no limitations on my domain. It still stays the same. My range, because I didn't actually move it up or move it down, my range still has that low end of being 0, and my high end, I'm going to positive infinity still. And then my horizontal asymptote, because I didn't actually move the graph up or down, my horizontal asymptote is still y is equal to 0, right? Because I'm still floating just above that x-axis. Okay, I'm just getting really, really close to it, approaching it, but I'm never crossing it. So then my last piece to this are my intercepts. And so you'll notice, like originally my intercept, when I put 0 in for x for my y-intercept, I was at 0 and 1 in my original. But now when I shifted that graph, I've came down. My y-intercept is actually getting closer and closer to 0, right? So in order to do that, if we look at this, I've got my original function. If I end up putting 0 in for x, if you want to find out what your y-intercept is, we always put 0 in for x, right? So if I look at this and go 2 times 3, now if I'm replacing the 0 for x, I really have 0 minus 4 is going to give me a -4 up there instead now, right? So now it's just a matter of finishing off our calculations to figure out that number. So take note, when we had a negative exponent up top, we always moved our base with that negative exponent down to the denominator to make it a positive exponent. So in reality here right now, I would have it looking like that with a 1 underneath. Well, this 3 to the power of -4, I'm going to actually shift that down to the denominator, because by doing that, this becomes a positive exponent. So now what I really have is I've got 2 over 3 to the power of 4. Okay, I made it as a positive exponent now by moving that base with that negative exponent down. So now I've got 2 divided by, well, 3 to the power of 4. Oh, what do we got? That's 27. That's 81. So I really have a y-intercept of 0 and 2 81s. I can leave it as that. I could change it to a decimal if I wanted to be, but that makes sense, right? Like, because I look at 2 over 81 is going to get me really, really close to 0, but not actually touching at 0. Questions on that? Cruz, how are you making out?
I'm doing all right.
Is it okay?
Yep.
Is it making sense?
So far, yeah.
Okay. That's a good sign. That's a good sign. Okay. Now, let's see. Let's do another one. I'm just looking to see where we want to go next with this. Okay. Let's just do the next one that we've got in line here. So same thing. We're starting with a new function now. But first, identify what your basic exponential function is. So you basically are looking for find your c, right? Find where, like up here, our c happened to be that 3 to the power of x. Well, when I look down here, again, I have that base of 3 in here. That's my base where I have my exponent to, right? So really, I'm still operating in that world of y is equal to 3 to the power of x, which actually makes it really great for us moving through this one, because that whole table of values that we did in the very first question, we're going to pull that back down because that doesn't change. We're still using that same base function that like we did in the first one. So rewrite that all down. We don't even have to do any calculations because we did all the work from the previous one. So let's just rewrite it all. And then we'll worry about looking at our transformations and how we need to, how that's going to affect our graph this time. I'm going to erase that piece of it. Okay. So now we've got a few things, and I always just work from left to right just so I don't miss anything as I go through these, right? So I look first is I've got a negative. I've got that lovely negative, and anytime I see a negative, either in front of my a value or in front of my b up here in my exponent, that's going to tell me I've got a reflection. Now, because it's negative, it's a negative a, I've got a vertical reflection. Okay, so that for sure, I know a vertical reflection means that my graph is going to basically reflect across my x-axis, right? So that's going to shift that. Now, I've got a half in here. So it's saying a is a half, right? So a equals 1/2. That's telling me, again, because it's a and it's outside of my function, I have a vertical stretch by a factor of 1/2. Okay, so I've got that going on. So I've got the vertical reflection, I've got a vertical stretch. So that's all I've done is taken care of that negative 1/2 out front, and that's given me these two pieces of information. Now the 3 does nothing for me right now because that's just my base function of my exponential. So I'm going to move over to up in my power. In my exponent, I've got a 1/5 x. That 1/5 is my b. Okay, so that's my value in front. Now remember with that, that's going to talk about, that's my horizontal. So I'm within my function now. So this is a horizontal stretch. So B is only looking at either if it's going to be a horizontal stretch or reflection. If this happened to be a negative 1/5, then I would say I have a horizontal reflection as well. But it's positive. So I'm just only focused on a horizontal stretch right now. Now, it's 1/5. It's the opposite of that. So this is a horizontal stretch by a factor, not of 1/5, but by a factor of 5, right? So you're going to take that 1/5 and you're taking the reciprocal of it. So you're really flipping that fraction. So if this happened to be just a 5 in here, then we would take the opposite of that, and that would make it a factor of 1/5. Okay, so your B, you're always taking the opposite, the reciprocal of it. And then I move myself over and I've got this -5. It's not up in my bracket or up in my exponent. It's down with the rest of the function. So this is my k value. Now that again is outside of my function. So this is basically back to, hey, we're working with a vertical. This time it's a vertical translation. So it means that we're shifting. So we're going to shift our graph. It's a vertical shift, so that means either I'm shifting it up or down, depends on which way. Now, because it's negative, that means I'm going to shift down 5 units. So there's a lot of things going on in this graph. We've got a lot of things that we have to account for when we go to do our mapping notation for this. Any questions, anything that you need me to clear up in terms of our translations that we've got down here?
Where'd you find the 1/2 for the vertical stretch?
Right here. This here.
Oh, just from what's in front of it.
Yeah, just literally that's your A right in front of it. Yeah.
And
sorry, go ahead.
sorry. I was just gonna ask, the negative on it doesn't affect it in any way?
The negative comes up in the vertical reflection. That's why I wrote vertical reflection down.
Okay.
Because A equals negative. Okay.
Yeah.
That's why I've got that there. Yeah.
Okay, that makes perfect sense.
Okay. Josh, you had a question?
That was the same question. Thanks, Chris.
Okay. Okay. Perfect. Okay. So now that we've identified all those translations along the way, let's create our mapping notation, just like we did in the first example, right? Let's figure out what is going to affect my X and what is affecting my Y. And once we get that all figured out in terms of like the mathematics behind it, then we can take all our original ordered pairs and transform them. So a vertical reflection. So when A is negative like that, anything vertical is going to affect my Y. So I look at this first one as a vertical reflection. It's going to affect every single Y value by taking the negative of it. Oh, hang on. Don't write the Y down here yet. So I know it's going to be a negative. It also has a vertical stretch by a factor of 1/2. So this is also, because it's vertical, it's affecting my Y. So that means every single Y value, I'm taking the negative of it and I'm timesing it by 1/2. Okay, so I'm taking 1/2 of it. And then the other vertical piece that I got going on here is that I'm going to shift it down. So I'm moving it down 5 units. So that means every single Y, I'm taking the negative, timesing it by a negative 1/2. And then after that, I'm subtracting 5 off of it. This is a lot happening to your Y value here. So that's why. Now, the last piece we have to account for is the horizontal stretch. That horizontal stretch, because it's horizontal, it's affecting your X. And it is stretching it by a factor of 5. That means, because it's a factor, it means it's multiplying every X value by 5. Okay, so once we've got this, so we've accounted for our vertical reflection, our vertical stretch, and our vertical translation. That's all showing up here in my horizontal stretch. One lonely thing happening. Sometimes you get it, you guys, where it's only affecting either everything is happening to your Y value and nothing happens to your X. That can happen. So it just depends on what you got for transformations happening. Okay, so now what we want to focus on now is let's go through and let's make all the new transitions to our points. So in this case, every single X value is just going to get multiplied by 5. So -2 times 5 gives me -10. And then I take my, oh, these get fun now. Okay, so now I've got a 1/9. And I am going to times it by a -1/2, which is actually, so if I've got a 1/9 and I times it by a -1/2, that's going to give me a -1/18. And then I'm subtracting a 5 off of it. So in these instances, I'm okay, you guys, if you just do these as decimals. I don't expect you, because ultimately, in order to go to graph it, you kind of need to know the decimal. It's way easier to work in a decimal as opposed to a fraction moving through this. Okay, so a -1/18 subtract a 5, you're going to end up with a -5.16 repeating. So you're looking at this going, oh, it's just a little bit, you know, beyond -5. Then I put the -1 in, I'm going to get a -5. And again, I've got a 1/3 times the -1/2. And then I'm going to subtract the 5, which is going to leave me with a -1/6 subtract 5, which in this case think I missed a spot in my questions. Did I change something? I don't think this one is negative 5.16. Hang on. Something is screwy. Oh, this one is
1/9.
This got to change. 5.06. We're going to leave it at like that.
+1.
And then the next one, I've got 1 divided by 6. This one is going to be negative 5.16 repeating. And then I put 0 in. I'm still going to get 0. And so now I've got negative 1/2 times 1 minus 5. So that's a negative half, subtract 5. So I'm at negative 5.5. And then if I put in 1, I'm going to get 5. And I'm going to put a 3 in. So that's going to give me negative 3/2 minus 5, which 3/2 minus 5 should give me negative 6.5. And then my last one, again, I'm going to get this time a positive 10. And now I'm putting 9 in. So I'm going to have 9 times negative 1/2 minus 5, which gives me negative 9/2 minus 5. Which should work out to, that's like negative, this is a 5. Negative 4.5 minus 5, so that should give me a negative 9.5. Oh, and I ran off my paper. Sorry, guys. So we've got a shift in things here, right? So now we've got to actually plot our points, what we've got going on. So I'm going to go over negative 10, but I'm going to go down 1, 2, 3, 4, 5. So just past it a little bit. And then I'm going to go to 5, 1, 2, 3, 4, 5. And then I'm going to go down again, just past a little bit further. And then I'm going to go to 0, negative 5.5. I'm going to go to 5, 1, 2, 3, 4, 5, and negative 6.5. So down there. And then 10 takes me to negative 9.5. So what I start to get is this graph that looks like this. And at this is going in this direction, right? It's going on that way. So take note. You've got arrows on both ends that indicate what's, that it's going to keep going on forever and ever. Now your question, we still have to determine, okay, so now we still want to go through our domain, our range, our horizontal asymptote, and then my intercepts. Questions so far before we do the rest of this, just to make sure you're kind of all on the same page?
I got it. I'm just catching up on the graph.
Okay, I'll hang on for a moment to get you guys so you've got it caught up. Bruce, how are you feeling?
I understand finding the coordinates and that. The only thing I'm kind of confused about is that little bit near the bottom of your page. I believe I missed that going from, that piece. What does that represent within the graph? Or was that just you finding the equation for the actual piece?
I was just finding, these are all my little calculations along here.
Oh, okay. All right.
For my Y's.
Okay, then I completely understand. Okay, that
calculator, I was.
Yeah, that makes complete sense. Okay.
Okay.
Thank you.
They're all different ones.
You saw my brain activity there for a moment of everything working before I,
Doesn't matter.
Okay. So the domain here again, And so if this is our spread of our x values, and we want to see if we have any limitations on our x values, x meaning we're going across left to right. In essence here, we have no limitations, right? This graph is going to go on in this direction forever and ever. And technically it's going on in this way. It's just angling, but still going on to the right. So our domain here still holds true. It's negative infinity to positive infinity. Our range is going to look a little different with this one, isn't it? What is our range going to look like? Any guesses? So
-5 to -infinity.
yeah, so if I'm looking at this in terms of always starting with my low end first, I'm going to say my lowest is going to be negative infinity, and the highest that I'm going to have is -5. You betcha. That's exactly what we want to see. And I've put a rounded bracket on here because we aren't actually going to touch at -5, right? It's just going to approach -5 and just ride along. It's like you approach the wall, but you don't actually get up on the wall, right? So we're going to keep this just as an open interval here instead. We're going to use a rounded bracket. Okay, my horizontal asymptote. Your horizontal asymptote is going to come from your range, right? So you see what your high end, where that is. Okay, it's going to negative infinity, but it's approaching that -5. So your horizontal asymptote here is that -5. And guess what? That actually, you can find that right back in your original equation, right? You can identify what that horizontal asymptote is right back in your original, which we could have predicted that. So that's going to tell us if we move this graph any bit up or down, that's going to shift our horizontal asymptote. It changes as well. And then the last piece we have to worry about is our intercepts. So same thing, we aren't even close to the x-intercept, but we did cross our y-intercept. So when we look at our y-intercept, always go back and look at your transformed table that you have. If you've got an x equals 0 in there, you've just saved yourself a step, right? Because right here, x equals 0, when x equals 0, you've got y is equal to -5.5. So in this instance, we didn't even have to do any calculations. We've got our y-intercept of -5.5. If not, if it didn't show up in this particular graph or in our table, then we'd come back to here and we'd find it the same way. We'd put 0 in for x, and we'd go ahead and solve all of this out and figure out that we would still come back out to that same process of getting -5.5 as an answer. So, whoops, drop my pen. So this here ends up being my y-intercept. How does that feel?
Good. There's lots going on in this one, but it's good because you get to see the reflection, or where the reflection will be.
Yeah, and that was important, right? Like that's kind of purposely why I did it. So you're seeing lots of all the transformations actually happening in this, right? There's only a couple that we didn't approach, but the method, part of it is once you get this done, once you've figured out what those transformations are, then it's a matter of going back to your original set of points and plunking in and figuring out what your new set of ordered pairs are, right? So that you can plot them. So this is half the battle right here. Once you can get that mapping notation, then you're set.
Spilled juice everywhere.
Okay, I think I'm going to stop there for today because I think with those two examples, now take note with these questions, like both of these worked out to where we had a that basic function of, oh, I'm off my paper, basic function of y is equal to 3 to the power of x. Okay, now if I'm just looking ahead, yeah, here. So if we looked at this one, I won't actually do the question, but if you look here in this instance, This one is going to work out your basic function you're going to start with is y is equal to 2 to the power of x, okay? Because that represents your c in here. So that piece changes what your original set of functions or your ordered pairs will look like, right? The rest of it, you still are addressing if you've got an A or an H or a K, and you're still working through the same processes we would have had before. So all of that doesn't change. Just this base function changes, which will change your original product of your table and then shift everything accordingly.
On the one underneath it, where you've got the 2 in there for B,
Yep.
you're still going to be using the same base function because you're just disregarding that B to find your base.
Okay, so this one is an interesting, your 2 is your base here. That's your C here, right?
Right. I meant the 2 in the exponent.
Yeah. Okay, so let's look at that. So this is your base function of 2 to the power of x. Now this piece in here, you want to account for this. So when we do these ones, so we've got the 2, I want you to factor out. I'm going to put factor here.
Right. So it'd be 2 times 1 plus 3 or whatever, x plus 3.
You're going to have the 2 times the x plus 3. You have to factor that out so that you get your b out front, and then you've got your x plus your 3 inside, right? So definitely got to pull that 2, because we never want that x to have a value in front of it. You're going to pull that value, take it out, divide it out. Okay, so that's why we factor that. Absolutely. And then we'd have this as, was this a minus in here? I can't even remember what that.
Yeah.
-5. Yeah, definitely. And then you could continue on your way. Yeah.
Perfect.
So in this case, we have no a in here, right? Our a is equal to 1, so that does nothing to our graph. So we have a b, we have an h, and we have a k that we would have to contend with there.
Perfect.
Yeah, good questions. Good questions. On that note, that basically now takes you through, you can do the next assignment in your notes package. I think it's assignment number 2. And then we will be basically, when we come back after Easter break, we have one more section to worry about and work with on that. So then we're kind of done this unit.
Awesome.